Today we have specialized engineering for the things that surround us. We have mechanical engineers for cars, electrical engineers for computing systems and chips, civil engineers for buildings. Do we have engineers specializing in medicine and biology? Do we even need them? Today, in the next 6 minutes and 45 seconds, I will illustrate the need for bioengineering. Research in health and the life sciences aims to bring solutions for better health. And there is the process biology does these wonderful discoveries. And through this process, translation, we take this knowledge into solutions for the patient. And one example is the drug. But we need to accelerate this process. It takes a long time and a lot of investment to take this technology into the patient. So the question is, how can we improve the translation process? And importantly, who are the professionals that can do this improvement? If we look at the natural sciences, physics, like biology, is a science that discovers. But translation happens from engineers because they add this problem-solving skill to that discovery. So we need to bring a similar problem-solving skill with specialized engineers in medicine and biology. And this is what we define as bioengineering. And in fact, we educate 14 engineers to 1 physicist today, but only 0.07 bioengineers to 1 biologist. And that might explain also why translation might not be as fast as we want it. And if you go to a campus across Europe or here in Germany, you will see a faculty of physics, a faculty of electrical engineering, mechanical engineering. In fact, in a technical university, you will have faculties for so many different things: civil, chemical, industrial, computer, software. And yet, it would be very difficult to find a faculty that specializes engineers to biology or medicine. There's virtually no faculties in Germany and also across Europe, very few, less than 10. And this is when, in Asia, this is one of the fastest rising engineering disciplines, in the US already very well established. So with the help of centers across the Helmholtz family in Germany, and of course the great support of the headquarters here, we put bioengineering on the agenda of Helmholtz, and we identified 6 flagships that map our strengths under bioengineering. And why 6? Because the drug is not the only translational tool. There are so many other technologies: cell protein engineering, implants. I will give you very quickly 2 examples today. One from continuous healthcare, and the other from high throughput screening of organ on a chip. What is continuous healthcare? So we all have memories of a red light appearing in the dashboard of a car. And by the time the red light was there, steam was already coming and we could see cars stranded by the road. What happens today? Hundreds of sensors. They measure everything. You get an orange light, you get service, and you do not have a catastrophic event. This is the concept we want to bring in medicine. We want to move away from symptoms-based medicine. Symptom is already a late event. And have sensors that they measure information on health continuously or frequently, and through AI, through artificial intelligence, finding your health status or the progression of health. But the big problem is how. These smartwatches, they're not that smart. They do not really measure information that can really see disease. And one of the reasons is a lot of the smartwatches you may have in your forearm now use light. But the light, when it gets in tissue, gets diffusive. You do not see the bone, you do not see blood vessels. We have invested and advanced a technology called optoacoustics and pioneer optoacoustic mesoscopy. We illuminate with light, but instead of using detectors to look at light, we listen at light propagating in tissue with ultrasound detectors. And this converts this diffusive image to a high-resolution image. What you see up there is a cross-section of the human skin. It's a technology receiving many awards also across Horizon 2020 in Europe. So we now take these images, we process them with artificial intelligence, and we extract up to 200 morphological, metabolic, functional markers. Not one or two that your phone gives you, but more than 200. And we show already that these are informative markers because we do clinical studies, and we see that we can track disease. This graph shows diabetes progression with a skin scan. This is a technology that we engineer with spin-offs out of Helmholtz Munich we have placed all over the world. In a recent analysis, we found that 55% of world's clinical studies with optoacoustics are done on our platform. What we do now, under the bioengineering agenda of Helmholtz and synergistically with other centers across Germany, we try to miniaturize this technology and take these big systems truly into your forearm and into your home. And here comes the next example. Bioengineers in Helmholtz engineer mini human organs, organ on a chip. And what we want is to couple now this advanced sensing technology with robotics in order to do high throughput screening, essentially testing drugs or other hypotheses day and night to accelerate also the drug discovery pipeline. Made in Germany logo is known to indicate quality and excellence. Excellence in engineering. And this excellence in engineering is what brings these wonderful technologies and products that propel economy, and they also give solutions to societal problems, leveraging the wonderful discoveries that are done in physics and chemistry. We need to get the same problem-solving skill in health, accelerating that translation process and improving our health. Thank you very much.